supercomputers can process information about 100 million times faster than a PC, but to power and cool the massive system can also cost millions of dollars. Researchers are working on an energy-efficient biological supercomputer, which they hope will change the way supercomputers are built. The team replaced electrons in a chip with a substance that gives human cells energy with the hopes of cutting costs and keeping the system from overheating. The computer consists of a specifically designed, nanostructured network explored by a large number of molecular motor-driven, protein filaments. Researchers from McGill University included in the study published in the Proceedings of the National Academy of Sciences. This system is highly energy efficient, thus avoiding the heating issues limiting electronic computers. The team used adenosine triphosphate, ATP, as the power source for the advanced computers, and the model created is much smaller, uses less energy, as it uses proteins present in all living cells to function, reports McGill University in a recent press release. "We've managed to create a very complex network in a very small area," said Dan Nicolau, Sr. "This started as a back-of-an-envelope idea, after too much room I think, with drawings of what look like small worms exploring mazes. This new concept birthed from a combination of geometrical modeling and engineering know-how, on the nanoscale. This is this first step in showing the capabilities of biological supercomputers and how they will perform." The circuit looks similar to a busy, but very organized, city with roads as seen from an airplane. Just like in a city, cars and trucks of different shapes and sizes, powered by different types of motors, are zipping around the roads, consuming the fuel they need to keep moving. In the case of this study, the city is a chip about 1.5 centimeters square in which the roads have been etched into. Researchers replace the traditional electrons that are propelled by an electrical charge, with shoestrings of proteins that travel around the chip in a controlled fashion powered by ATP. All these features will keep the system from becoming too hot and keep energy use down to a minimum. We implemented the proposed computational approach with biological agents that satisfy the following requirements. The agents, proteins, are available in large numbers at negligible cost, are self-propelled and thus do not require a global, external driving force, operate independently of each other to ensure parallel exploration, have small dimensions to enable use in high-density networks with high computing power per unit area, move rapidly to maximize computational speed, and move in a predominantly forward direction, to ensure low error rates, according to the study. Now that this model exists as a way of successfully dealing with a single problem, there are going to be many others who will follow up and try to push it further, using different biological agents, for example, said Nicolau. It's hard to say how soon it will be before we see a full-scale biosupercomputer. One option for dealing with larger and more complex problems may be to combine our device with a conventional computer to form a hybrid device. Right now we're working on a variety of ways to push the research further. Last December, scientists revealed they had developed an electronic chip made of both biological and solid-state components with the hopes blending senses with electronic components. They combined solid-state complementary metal oxide semiconductor, CMOS, integrated circuit with an artificial lipid bilayer membrane made of ATP-powered ion pumps to create a biochip. This breakthrough study was led by Ken Shepard, Lau Family Professor of Electrical Engineering and Professor of Biomedical Engineering at Columbia University. In combining a biological electronic device with CMOS, we will be able to create new systems not possible with either technology alone, said Shepard. We are excited at the prospect of expanding the palette of active devices that will have new functions, such as harvesting energy from ATP, as was done here, or recognizing specific molecules, giving chips the potential to taste and smell. This was quite a unique new direction for us, and it has great potential to give solid-state systems new capabilities with biological components. Although there has been a breakthrough with these new findings, Shepard said that CMOS solid-state electronics do not have the ability to perform or replicate certain functions of living systems, such as tasting, smelling, and the use of biochemical energy sources. Living systems perform these functions with their own versions of electronics based on lipid membranes and ion channels and pumps, which act as a kind of biological transistor. Charge is produced in ion form, which carries energy and information, and the ion channels control the flow of ions across cell membranes. Solid-state systems, such as those in computers and communication devices, use electrons. Their electronic signaling and power are controlled by field effect transistors. Living systems store energy and potentials across lipid membranes, but in this case they were created through the action of ion pumps. ATP is used to transport energy from where it is generated to where it is consumed in the cell. The team packaged a CMOS integrated circuit with an ATP harvesting biocell to begin building the prototype. In the presence of ATP, the system pumped ions across the membrane, which produced an electrical potential harvested by the CMOS integrated circuit, IC. We made a macroscale version of this system, at the scale of several millimeters, to see if it worked, Shepard said. Our results provide new insight into a generalized circuit model, enabling us to determine the conditions to maximize the efficiency of harnessing chemical energy through the action of these ion pumps. We will now be looking at how to scale the system down. By performing this on a molecular level, scientists were able to isolate the desired function and interface this with electronics. We don't need the whole cell, Shepard explains. We just grab the component of the cell that's doing what we want. For this project, we isolated the apases because they were the proteins that allowed us to extract energy from ATP. Ability to build a system that combines the power of solid-state electronics with the capabilities of biological components has great promise. You need a bomb-sniffing dog now, but if you can take just the part of the dog that is useful, the molecules that are doing the sensing, we wouldn't need the whole animal, says Shepard.